Okay, we will continue again. In last lecture, we have derived the partition function of one particles having a continuum energy. So we have transformed from the summation symbol into integral symbols to represent the condition belongs to particles having a continuum energy. Example of that particle is a particle in gas where each molecule or atom in the gas assembly can have any energy. They can have a kinetic energy from 0 to infinity. So we don't have a quantum number to define the energy of this particle discretely. We have we have obtained the expression for the assembly, for the particle partition function. Partition function or particles of continuum particle energy. We have obtained that the partition function of particle is 1 over a power 3 and then integral exponent negative particle energy over kT, and this is dx, dy, dz, dpx, dpy, dpz. But again here, the meaning of this one symbol is a sixfold integral. This is the meaning of this one is 1, 2, 3, 4, 5, 6 dx, dy, dz, dpx, dpy, and dpz. So this is the simplification of the expression, but we have to understand that it means a sixfold against x, y, z, px, py, pz. Now we will apply this expression for determining the partition function of a gas particle. Now we focus on the ideal gas. This is the most simple gas, ideal gas. In assembly, this assembly containing gas particle, and this is assumed to be ideal. What is the meaning of ideal gas? The ideal gas means that the particle inside the gas have no interaction between particle. No interaction between particle inside the gas. So the particle in the gas has only kinetic energy. No interaction between particles. So the energy of the particles, the potential interaction energy, ignore interaction energy. Interaction energy, ignorable, and the energy of the particle is only the kinetic energy. Then the particle has only kinetic energy. The particle is free, no interaction with another particles. So the particle only have kinetic energy that depending on the particle speed. This is the particle square of the particle speed or velocity, and we can write this one as half of m vx square, vy square, and vz square. We can also write this one as px square over 2m plus py square over 2m and pz square over 2m. This is the kinetic energy of one particle in the gas, in the ideal gas, not in the real gas. But in case of another gas, what is the condition that a gas can be considered to be ideal? What is the condition of a gas can be considered to be an ideal gas? Ideal gas means that the particle has only kinetic energy, no interaction energy between particles. But another gas can be considered as an ideal gas if the kinetic energy of the particle is much larger than the interaction energy. Even there are interactions between gas particles, but if the interaction energy is much smaller than the kinetic energy, we can ignore the interaction energy and the gas energy as only kinetic energy. So, even there is interaction between particles, there are interaction potential, but if such potential of interaction is much smaller than kinetic energy of the gas, we can consider the gas as an ideal gas. To obtain this condition, there are two conditions to reach this condition of the ideal gas. First is the density is very low. If the gas density is very low, then the distance between gas particles is very large. Interaction between particles becomes very small, and it can be ignored compared to the kinetic energy. Another example is temperature is very high. If the temperature is very high, then the speed of each particle becomes very high. So the kinetic energy becomes very high, and it might be several order of magnitudes higher than the interaction between gas particles. So even the interaction energy is large, but if the kinetic energy is much larger, we can ignore the interaction energy, and the gas can be considered as an ideal gas. So ideal gas generally obtained at the condition where the gas density is very low or the gas temperature is very high. In both conditions, the kinetic energy is superior, is much larger than the interaction energy between particles. Now, we assume that our assembly is an ideal gas. Now, for ideal gas, the energy of ideal gas, energy of one particle is only energy equals to px square over 2m plus py square over 2m plus pz square over 2m. This is the energy of one particle inside the assembly of an ideal gas. So we have to apply this expression into the partition function of continuum assembly. So the partition function of one particle, partition function of one particle of ideal gas becomes just equal to 1 over h power 3. And then we have this is 6-fold integral. This is exponent minus, we apply this one, px square over 2m plus py square over 2m plus pz square over 2m divided by kt. And then this is dx, dy, dz, dpx, dpy, dpz. Now look at this integral. We will integrate this expression. This expression contains only momentum variable, ps, py, pz. This expression does not contain spatial variable, dx, dy, dz. So because this only contains the momentum variable, we can then separate the integration of spatial and of momentum. So we can separate this integration of spatial and then of momentum. over 2m over kt dpx dpy dpz. So only momentum will come together with this expression, and the spatial can be separated in three fold integral, separated fold integral. Now the integration is of x, y, z. This is the volume element of in spatial coordinates. So if we integrate these three-fold, we will have the volume of the gas. This is the gas volume. And now, again, let us consider this one. We can write exponent minus px squared over 2m plus py squared over 2m plus pz squared over 2m and divided by kt. We can separate into three multiplication. Ps squared over 2m, exponent means py squared over 2m over kt, exponent minus pz squared over 2m over kt. So the summation can be separated into multiplication. So this integral exponent minus ps squared over 2m plus py squared over 2m plus pz squared over 2m over kt dpx dpy dpz. These integrals, we can change this, we can replace this expression with the multiplication of three exponents. Because each exponent has different variables, only ps, only pvy, only pz, this integral can be separated into three, minus px squared over 2m, 2m kt, dpx only, then exponent minus py quadrat over 2m kt, dpy, and then exponent minus pz quadrat over 2m kt dpz. So this integral can be separated into three multiplication of three separated integral. Now, let us see here. The difference between three integrals is only in variable. There is p, px, dpx, py, dpy, pz, dpz. After integration is performed, from 0, minus infinity plus infinity, minus infinity plus infinity, minus infinity plus infinity. After we perform the integral, the variable p will disappear. So the result is independent of the variable momentum variable. The result is independent of momentum variable, They are only depend on the m, and t, and k. So after integration is performed, the three integral is the same. It's exactly the same. This integral is exactly the same because the variable, integral variable will disappear. It only contains the m and the k and t. So because this is the same, we can change the three multiplication into only one, exponent minus ps squared over 2m kt dps, and this is power of 3. So we don't need to calculate two odd integral, we only calculate one, and then giving power 3 of this one integral will result the total integral this one. So our result for the partition function of the one particle inside the ideal gas is 1 over h over 3 power 3, and this is the volume, and this is on the integral only one term, minus ps squared over 2m kt and dps, and this is power 3. And we can show here that the result of this one inside the bracket is square root of 2p kt. Please, you can use the Wolfram alpha. to calculate this integral. This integral, the result from minus infinity to infinity is 2pmkt. So the partition function of a gas particle in one particle in an ideal gas becomes v over h power 3 2 pi mkt, and then the power becomes 3 over 2. This is the partition function of one particle inside the ideal gas. So the partition function of assembly, partition function of assembly of ideal gas becomes very simple, obtained from the partition function of one particle. Large J is equals to small z power n. That means that v over n, h over tn, and then 2p mkt over 3 n over 2. This is the expression we require. We need the expression for the partition function of assembly, because from this expression we derive the macroscopic equation for the gas. Now the expression is obtained from the partition function of one particle inside the gas, and then we give power n to the partition function of one particle. We then obtain the partition function for gas assembly. Now, then in the next, we will use this expression to determine the equation for gas, as we have learned in the lecture of thermodynamics or statistical mechanics in bachelor, in undergraduate lecture. We will continue later.